Hello and welcome to our third webinar for today. This also happens to be our first webinar, which is a CEU session. So it's important, number one, that you be logged in on Zoom, which if you're viewing this video today, you should be. And number two, stay logged in all the way through the presentation today in order to qualify for your CEU. Now we'll go through afterwards and we get a timestamp saying when you logged in and when you logged off. During those two time periods, beginning and end, we would like you to be paying attention to the whole presentation. We hope you learned something today. And we're proud to present this to you. I know this has been some trying times, so we're doing a socially distanced expo, and we hope you've been enjoying it so far and hope you continue to enjoy it over the next several days. Today's presentation is over maximizing spray application success, and this is going to qualify you for One Drift Management CEU. And joining us today, we're going to go to him in just a moment when I get through introducing him, is Dennis Christie. He's a certified professional agronomist and a senior regional agronomist for our partners at Winfield United. Agronomy division is partnered with Winfield United. They make us stronger. They have a full line of agronomy products that we do offer in our retail centers. They're a tremendous support to us, and people like Dennis Christie are there to help us if we ever stumble or fall or need a little extra help. So through the whole cooperative network that we participate in, we have so many different services and intellectual people that allow us to bring these programs to you in the best way that we can. So we're going to turn it over to Dennis Christie now, and we thank you. And Dennis, it's all yours. We'll just get you loaded up on the screen.
All right, can you hear me?
Yes, sir, we can hear you.
Okay, very good. Well, Jason, thanks for all that. The one thing I think about this is we're talking about application success. I think that's the clear meaning of what we want to try to convey here is what is success and how do we make that happen. And it's the entire process of making an application, from deciding to do that to choosing the product to physically making the application and then being done and what's all that takes. So we're going to go through this. A lot of this we'll talk about some things that are in the past, and we'll talk about some things that are real current things that we have recently found out in our spray analysis system.
If you can go ahead and put that into presentation mode, you're on the, so that way we can have a full screen.
Well, let's see. I don't know if I helped us any there.
It's under the display settings in the top left.
Well, I don't have that.
Okay, we can go on like this. We appreciate it.
Okay, sorry about that. And I'll see if I can figure that out while we go through here. I start with this slide because Jason, I see display settings. Hold on just a second. Oh, I had them, but I can't get my mouse from one to another. So I wanted to start here and talk about this. When we add something to water, it changes what we're doing. It changes the size of the droplets or the way the droplets react. Try to get that out of the way. So this is a flat fan XR tip. 11003 operates at 43.5 pounds of pressure. and that's pretty much a standard testing pressure. So we're looking at the amount of fines that are less than 141 microns. So for kicks and grins, a human hair is about 100 microns. So 141 was what's in the literature, what's set up. So when we look at water, if we sprayed a gallon of water through this spray tip, we lose about 25% of that to droplet sizes that are less than 141 microns. Now, when they're that small, they may or may not contribute to our spray application. So that's just water by itself. We lose about a fourth of it. What's interesting in this is that we look across a lot of different products. We'll start on the left and look at 2,4-D ester. Well, we don't lose a lot to fines. It's better even than water, but we know that ester formulations of 2,4-D are very volatile. So we're not measuring volatility, just the size of the droplets. And then as we come over to and we see the red bar, that's water, we look right next to it and it's a quart of 2,4-D amine. Few more fines than what water produces. And again, just fines. And then we go over about 4 bars and we see 2,4-D amine at a pint, and we increase the number of small droplets that come out. So same chemistry.
Go ahead and share that screen again. We see your desktop.
Is that any better, Jason?
Make that work. You'll just have to scroll through them one by one.
Yep, okay. So as we look at that, rate makes a lot of difference with that. Same thing happens with dicamba over on the far right-hand side, about the 3rd bar from the right, 4 ounces, and then we go over about 3 more bars and we see dicamba that's 8 ounces. So rate makes a difference. So what we put in and the amount that we put in makes a big difference. How do we come up with this? About 10 years ago, we installed a spray analysis system. So we're talking about just the big red box there in that. It's got 5 components. We can mix up whatever chemistry we want to mix up, put it through there, and then the laser diffraction system. So that's number 2. And we see this thing that looks kind of like a mailbox just to the left of the computer screen. And that's actually a laser. So the nozzle, as we spray, it sprays horizontal. So instead of spraying down, it sprays to the side, and the laser goes through that. It's a low-speed wind tunnel, so it evacuates the droplets so we don't test them twice. The biggest thing about this was about $1 million investment just for the box. We developed patents around how we put it together and how we can test it. But his real big thing here is the expertise. Person that runs that, the way they set up the experimentation, that we tested multiple times rather than just one time. And so this has been a real informative system to give us information on what really happens with droplets, and droplets are carrying what we're pouring in the tank. So that one was put in about 10 years ago. Over the last couple of years, we've been installing a new system. If you can imagine, it's about the size of 2 semi-trailers, one stacked on top of the other. It's a high-speed tunnel, so we can do high-speed wind, almost replicating an airplane. We can spray over top of plants, even corn plants that may be 6 foot tall. We can look at boom type rather than just one nozzle. We can look at multiple nozzles through this. So we're going to be getting a lot of information and already have some. It's in operation now. That's kind of what it looks like now. And And there's also a second wind tunnel tied to this to get more information out. The first things first, when we make an application, we've got to think about calibration. And most of our labels tell us that rather than just pouring in so much per gallon, we actually need to put that pesticide on a given area. So calibration starts to come into the very first part of the picture. There's all kinds of different methods. Sometimes it's a rate controller. Sometimes it's calibrating by hand. There's all kinds of university sources to help us do that. And really calibration takes maybe 30 minutes and it helps us do it right. So it gives us the gallons per acre, how much we're putting over a given area with that specific nozzle that we're looking for, the pressure that we've got set up, so we can dial those things in as we calibrate going through that process. Then we look at our spray tips and we look at, are they uniform? Are they giving us what we want? Is something plugged? Do we have a really strange pattern coming out of that nozzle? Do we have leaks? Do we have screens that are plugged maybe with that as well? All those things we can kind of get from calibration as we start off. If we have pressure gauges set up, it can give us an idea of are the gauges reading correctly. There can be differences between boom sections, between the cab and the boom gauges, and all those things come into play and tell us really what's going on or what we're doing. Then we look for nozzle wear. We'll get into that in just a minute. The orientation, are they all relatively spraying the same direction? We can look at the flow rate of the nozzles. And really the nozzles are set up, if it's a 110.03 tip, it's going to spray about 0.3 of a gallon a minute out of that nozzle. So that starts to give us a little bit of indication of what we might need and what we're looking for. Overlap. We always prefer to have an overlap of the pattern, and that gives us opportunities if we have uneven terrain to get everything covered. And then it tells us drift potential. Is our pressure too high? Do we have the right nozzle in? Is the orientation bad? All those things, again, we get from starting that calibration process. So I mentioned nozzle wear. There's a graph in the back of one of the nozzle books that says after about 40 hours of operation, stainless steel nozzles can have about 8 to 10% wear. Now, it doesn't mean that our flow is going to be different because we may have a rate controller that's putting so much out through there, but it will have an effect on the pressure and the pattern that we get out of those. So that's from a stainless steel tip, about 40 hours. Some of the new plastic tips will outlast stainless steel. So when we look for tips, we don't always have to be looking for stainless. Some of the new plastics will actually better tips than stainless. So when we think about the application that we're going to make, in the back of our mind, at least, a lot of things go through. What's our target? What am I spraying for? Is it a weed, a disease, an insect? Am I putting on foliar and nutritional products? What is our actual target of what we want to do? How do we go about that? What's the goal? Is that a specific weed? Are we going after a specific type of weed in that process? Because the weeds are different. So if I'm looking at trying to control a grass weed, we know that those leaves are typically oriented upwards. If I'm spraying a broadleaf weed, those leaves can be horizontal, like you're holding your arms out. A droplet reacts different on those leaf surfaces. Is it a slick leaf? Is it a hairy leaf? How do we go about that? So what is the specific weed? What's the goal? What's that weed look like? How big is it? We start to think about those things. And then what are we spraying with? And when I mean that, I don't mean a self-propelled rig or something on the back of a 3-point. I'm really talking about what's our gallon per acre that we want, what nozzles are we going to use, what's our speed, those types of things that are going to help create a good application, uniform. And then what's the field look like? Is part of it under trees? Is part of it open? Is there a tree line? Is part of it uphill and the other part downhill? What's that field look like? How am I going to do that to create a consistency in what I'm trying to do? So how many constants are out there in that field? And again, we're thinking about this in our mind. We probably know it, but we're thinking through that. The more constants we have, the better we can be. So when we go through that process, how can we create consistency? And then how many variables? How do we overcome those variables? Maybe part of the field is open and I have more wind. Maybe part of the field has bigger weeds than other parts of the field, or different weeds. So how do I go about attacking those variables? And that's really what we're trying to get through and get to. And then what's at our disposal to gain as much consistency as possible? So we think of things as field speed. And if we're looking at field speed, maybe we have pulse width modulation that helps us change field speed but keep the same gallons per acre coming out the nozzle at the same pressure. Maybe we look at adjuvants to go in to help create consistency across how we attack those weeds or those insects. So those are the things that we think about in our mind, and how do we start to put all those together? So one of the first things is knowing the size, and obviously this is an issue that we all have. How big is that area? Well, there's a lot of technology that can tell us, but can we get to all parts of that field? Maybe part of it's muddy, maybe part of it's just inaccessible. And so we want to know the area that we're going to treat so that we don't have a lot of product left over in the sprayer. Because if we go in and we double things up, it can be harmful to the crop that we're trying to protect, or we can have other problems that come up through this. So we don't want to overtreat areas, and so knowing that area is very important as we get started, so we're not dumping stuff on the ground or trying to treat an area multiple times. So the other part is, what is the target? What are we really trying to go after? That's a real big piece. And so is it an insect, a disease, bugs, or not bugs, weeds? How are we going to attack that? And what do we need to do? And then we're all dealing with this issue of weed resistance. So I saw a picture a few years ago that came out of Nebraska, and it was a pigweed that had been sprayed probably for decades with the same chemistry in a grass field, and it's resistant now to 2,4-D. So we've got resistances coming in all the classes of chemistry. So how we rotate crops, how we rotate chemistries, use multiple modes of action is all a big deal. And if you've never walked in the field and seen this, where you killed part of the weed and then it's grown back, this is a really sickening sight. And it's one of the things that's on our mind today. It creates new technologies, really not getting any new classes of chemistry for this. So we have to think like the weed. We have to be smarter than the weed and look at all the options that we have to control and reduce weed resistance. Got this slide several years ago. It says from Dr. Brian Young at Southern Illinois. He's now at Purdue, but it says give weeds a finger. So this is just kind of a thought process here. We look at this and it looks like I don't know if it's Palmer amaranth or water hemp. 2 inches tall is ideal. And that 7 to 8, that's the number of growing points that weed has. So sites where that weed can regrow from. And we get to 3 to 4 inch weeds, and then 4 to 6 inch weeds, and then things that are bigger than 6 inches. There's a lot of growing points. Depending on the kind of chemistry we're using to control this weed, we have to hit and cover all those growing points to get control. Let me repeat that. We've got to cover all the growing points. So weed size becomes very important. It may determine what we look at for water volume, for the adjuvant package that we put in, or the rate of chemistry that we're applying to control that weed. And then we go back to, are we losing some of the spray like we showed in the very first slide? Are we losing some of that and not getting that here? All these things start to add up to fight resistance, but we're understanding and trying to think ahead of the weed. So hopefully that makes a little bit of sense. So let's talk a little bit about nozzles. This is a really good chart. There's a lot of things that you can read out of it. So it's kind of broken into quadrants up here at the top. We've got herbicide. So let's just stay in this herbicide column. We've got soil applied products, and we've got post-emergent products that are either contact or systemic. So let's talk about that for just a second. A contact product is not going to move throughout the plant. Not going to have a lot of movement. A systemic herbicide is going to be taken up by the plant and move throughout that to hopefully kill that root system and kill the plant. So differences there. Contact, things that are like gramoxone. Systemic, things like glyphosate or Roundup. Makes a difference there in what we're looking at. Then we get things that are contact and maybe a little bit systemic like dicamba. We talk about dicamba being systemic, but if we go back to those weeds, and we've all seen it with dicamba, we miss part of the weed, we miss the growing point, the weed grows back. So it is both systemic and contact. We need a lot of coverage. We look at 2,4-D. I look at 2,4-D as being more contact. The difference between 10 gallons per acre and 20 gallons per acre with 2,4-Ds can be pretty big in what we see in control. Same thing is if I look at 2,4-D with really large droplets, doesn't work as well as if they're smaller droplets. So that takes us into this line, and we see a Turbo T nozzle. Those are big drops, really good for soil applied, and they're good for systemic product, but they're not any good for contact. We go down to the next line and we see an XR flat fan type nozzle, really good for contacts, and they're okay for systemics. They're going to work there as well because we've got good coverage. So that makes a lot of difference in just how we look at the chemistries, how they work in the plant, as to what nozzle we're going to try to use with that. Then we go into fungicides, and I want to make the same comparison here between contact and systemic, with the difference being this with fungicides. Most of the fungicides we're using today, especially the strobilurine type products, are systemic, but systemic means it moves from the top of the leaf to the bottom of the leaf. So it just moved from the thickness of the leaf. Maybe it moved out the leaf a little bit, but usually not a lot. But they're certainly not spray the top, it gets down and works in the bottom. It doesn't work that way with systemic fungicides. Insecticides are more like herbicides. If we get them in the plant and they move throughout that plant, they're going to be systemic. Most of the insecticides we have today, however, are moving towards the contact type of control method. Then we look at drift management, how the nozzles rank there, and then PWM is pulse width modulation. So the nozzles actually pulse in a fashion across the boom where they're off and on, and we can change that frequency high or low, and it helps us with varying our field speed to keep a constant pressure and constant water volume out there. And if we look at that, where we see nozzles that have air induction, so the Turbo T's in this, the AIXRs and the AIs, they're not good for pulse width modulation because we can't suck air in. They're an air induction nozzle. We can't suck air in fast enough. Those nozzles may be pulsing every 1/10 of a second, and we just can't get that air to draw in fast enough. So what works there with pulse width modulation are the non-air inducted nozzles. So some of the T-jets, some of the Greenleafs, some of the Wilger, we have choices there depending on what we want to do. But again, we look here and say, what is our target? How am I going to go about doing that? What's the chemistry that I'm going to use? And we start to make a nozzle decision. My point here is there's really not one nozzle that's good for everything. We have to think about what we're doing. So we're past those days where we can throw it out there because of weed resistance and because of economics and what we're having to do. So we have to look at different nozzles to do a different job. And that's important as we start to go through calibration and what we're choosing. So these are all Turbo T air induction. The hole that's on the side of the nozzle, that's where the air comes in. And so we look at these nozzles and we look at the pressures that these nozzles can operate under, all the way from 15 up to 100. And what's important here is we can choose a different color, which is a different size orifice. And it tells us the gallons per minute that come out of that. So I said number 3, and this one is at 30 PSI, about 0.26, at 0.3, at 40 capacity. I'm sorry, there's ounces per minute. So then we look at speed and we get a gallons per acre. What's important from this chart is droplet size. So not only can we determine what our gallons per acre is and what nozzle we need based off the speed and the pressure, but also the droplet size. So anything below 60, we get an ultra coarse droplet that comes out. Go back to the previous chart, not going to be good for contact products. As we move up and we run this from 70 up to 100 PSI, it's an extra coarse droplet. So they get to be a little bit smaller, all based on pressure of the same nozzle. I hope that makes sense, but pressure determines droplet size as we choose a nozzle to get to the GPA that we want to try to work with or the speed that we need to run. We also look at the operating pressure to make sure that we're doing what we want to do and get out of that nozzle what's intended. We look at cropping systems, and of course we've got new technologies coming in the row crops. And so this is a picture of cotton. On the left is a very low, a 1/10 to a 50th of the rate of dicamba, labeled rate of dicamba applied at first bloom. And we see some damage, but not a tremendous amount. Of course, this would be more of a conventional cotton. But then we look to the right and we see cotton with 2,4-D somewhere between 1/10 and 1/250th of the rate applied at first bloom. And of course, we know 2,4-D on cotton is just is just on conventional cotton or non-enlist cotton is very damaging. So we look at this and think, well, what kind of drift? If we have any drift, what's that look like? Is it somewhere in the 1/10th to 1/250th? Probably so. So what kind of damage can we get out of that? So the cropping system, the traits that we have, now we're getting crops with multiple stacked traits to help us with the resistance issue. But those come with different things. So if we look at this, and we've got Liberty in the 2,4-D cotton, and possibly, well, it'll be in the dicamba cotton. Liberty requires a different droplet size than what dicamba does, or it requires a different droplet size than what glyphosate does to be effective. How do we do that together? Well, I don't know that we do. I think that might be two applications for those chemistries. So it really, really depends on trying to put all of this together to become successful. So again, nozzle selection, lots of different manufacturers out here. There's more than we've got listed. I think there's 3 charts here. I'm going to jump to the T-Jet technologies. And we look up here at the AI nozzles, and these are approved for the extend cropping system, whether that be cotton or soybeans. So dicamba and glyphosate. The AI, if we're running an air induction tip, it tells us which tips are approved, but it also tells us the pressures that those can operate under. So this one has a fairly narrow window between 30 and 40 PSI. We go to the Turbo T air induction nozzle, same size as the AI here. We can run that between 20 and 60. We change to an 04 tip, and it goes up to 63. So again, this is what's approved based on those labels. What tip we're running, is it approved, and what are the pressures that it can work under? Again, there's some more ranging from 30 to 90. We move to the enlist system. It's the same type of situation. They've just got a little bit different chart where we can choose our tip here that's approved, and then it tells us the operating pressure for that specific tip. And this would keep us within the label recommendation. So that's a little bit about nozzles. There's a whole lot more. We'll try to stay close to time here and start talking about tank mixing. Again, when we start talking about tank mixing, is it one product or is it multiple? Most tank mixes anymore have, it's not uncommon to see 4 or 5 different products go in the tank, and sometimes even more than that, depending on what we're trying to do. So is it the right product for the right weed at the right size of the crop stage? There's a mixing order for all these products. It's always on the labels. There's adjuvants that are required that goes in. We've got to have the right nozzles to go with all of this. So if that is our stopping point, maybe we look at even 2 different applications. So hate to say that, but that's kind of the world that we live in today with what we've got. So we want to make the right application, but the right application is a successful application, and we leave everything in the field where it needs to be. So unfortunately, over my years, I've seen all of this, and it's never a pleasant sight. You know, even if it's foam issues that run out of the top of the tank, we can have separation, or we can have what I call cottage cheese. And then you get actually this crystal that packs in those filters. I've seen that. That's ugly. And then you get the slime over on the bottom. And these are never pleasant, never, ever pleasant. But what I do want to make sure that I point out here is getting this stuff out of the tank and getting it through the system is just the first part. That's the goal, to get you to the end game of cleaning this stuff out so it's not a problem in the next tank load, figuring out what went wrong and how we do this. And this can simply be mixing order that causes these, or it might be incompatibility, or it might be the water quality that we're using. All those things make a difference. So if we mix 28% UAN nitrogen solution, or 32, and we put that with a 2,4-D amine, it's going to make cottage cheese for you. I'm just going to tell you about every time that's going to happen. Obviously, if we can get it out, there's reduced activity from that. But we also can have antagonism sometimes when we mix a post-grass herbicide with a broadleaf herbicide in these crops. So the same is true, it says, in soybeans, also in cotton. If we're trying to use something to get out Roundup-resistant corn in Roundup-resistant cotton, so we put in a clethodim or something like that, and we do that with a dicamba, we're going to have decreased grass activity. So we're going to end up upping the rate of our grass herbicide to get over that antagonism, or we're going to make two different applications. Fertilizers and bromoxone, sometimes we have problems there. And then all of this can lead to toxicity to the crop because we're not getting a consistent, uniform broadcast application. Maybe there's hot spots out in the field that develop. So as we think about that, even going back to slide number 1, where we have different viscosities of products, some are thicker or some are thinner, all those can have a problem in the tank if we're not keeping agitation going and keeping that product mixed well so we don't have those hot spots. Water quality makes a big difference. Temperature, yes. Now, South Texas, your water is probably never really getting cold. So that's something that's probably on our side. But can we have dirty water to deactivate some pesticide? Yes. Same water that's drawn out of a pond that's not good clean water, and it'll deactivate glyphosate in a heartbeat. Water pHs make a real big deal, but the biggest thing there is when we add it to the tank, does it affect our pH and what goes on there? Same thing with soil. We have a high soil pH. Some chemistries will last longer. As we lower the pH, those chemistries break down quicker in the soil. Same thing happens in the spray tank with the water pH. So mineral content, herbicide deactivation, we all know that with glyphosate, which is why we use some sort of ammonium sulfate to counteract that issue. Mixing order, Wales or Dales is a system that we use to talk about this. The biggest thing here is let's make sure that we read the label to give us the mixing order and become clear with that, because it can really give us problems. Tank contamination, probably the biggest area of complaints that I get involved with or discuss with people come from tank contamination. We have more post applications that are happening. We're using a lot more different chemistries. They can damage crops at very low rates. And so if we don't clean that tank out, once we finish, and when I say finish, before we turn everything off and go to the house, that tank needs to be cleaned out just as soon as possible. If we're changing to another pesticide or to another crop, it needs to be cleaned out. We have products today that work like tank cleaners, so they'll clean other things out of the tank, out of filters, out of booms, whether they're stainless booms or hoses. We think about gaskets. We think about things like threads that are inside the system. All those can collect things. not just the tank. The tank's pretty easy. Cleaning out that system is really, really important. And as we get into the season, there's a lot of stuff going on. We're rushing to the next event, but we've got to think about those tanks, know what we've got. Part of that's record keeping of what was in that tank last. And then we always have concerns over what to do with the rinse site. So a lot of the systems anymore have some sort of spray tank cleaner on the system so that while you're in the field, you can clean that tank out, spray it right over top of the crop, which is where it was intended to go. So if there's nothing else out of this presentation, we need to think about what can happen after we make the application and the negative effects, and that usually comes back to cleaning something out of the tank. Injury, again, most tanks today don't have one single product in them. They've got multiples. And so as we go into technology crops that have dicamba or 2,4-D or Liberty or Roundup, those things have to come out of the tank when we finish. And so some of those that are growth regulator type, like dicamba, 2,4-D, can really cause problems to the next crop. Then we've got products that are very low use rate. We're talking about maybe as low as 1/10 of an ounce per acre. And so that can have a big impact on the following crop. And then thick formulations, all these things combined, again, usually not one product in the tank, but multiples. So cleaning that tank out is really, really important. So let's now talk about what happens to that droplet. So we're spraying out in the field and we see it go from the nozzle down to the target leaf or to the ground. In that 24 inches from the boom to the target, there's a lot of things happen. We can very easily in our geography lose 2/3 of the size of that droplet in that 24 inches. When it's warm, when there's a little bit of wind, when the humidity's low. Those things, so we make smaller droplets so droplets move. So we don't want to miss the target. We want to keep it where we want it to be, but more success relies upon getting it to the target that we want it to. So as we think through that, it says here that fine droplets can blow away. Remember, 100 micron droplets about the thickness of a human hair. So that thing's going to move. If we look down to the chart and we look at vertical deceleration in the distance, and we look at 100 micron droplet, once that droplet moves about 9 inches out of the nozzle, it becomes a floater. It no longer has positive movement. It's up to the environment. So we want to avoid those small droplets. Now, the thing about it is every nozzle, doesn't matter what one it is, they create some droplets that are small, some that are bigger. It's just the way it is. They're not perfect. Every droplet that comes out of that nozzle is not the same. So we want to try to unify or put as much uniformity to those as we can. That will help us with deposition, with drift, getting it through the canopy, overall success. So this just shows us that based on the size of the droplet, how far it can move. That's a 10-mile-an-hour wind. We might think that's no wind at all, depending on where you are. So droplets can certainly move great distances. We see that here, not a pretty sight. We could have avoided that. So one of the things when we talk about droplets is VMD, which is volume median diameter. And what that is half of the volume. So if we have a 1,000-gallon tank and we've got this nozzle and this pressure that we're using, and we know the size of the droplets that are coming out, the VMD is the size of the droplet, where half of the volume of that tank, 500 gallons, is smaller than the VMD, Half of it is larger than the VMD. So we are creating different size droplets that come out of that. And when we look at the VMD, it gives us a relative number like 300, or that's in microns, or 400 or 600, where half of the volume is less than that, half the volume is above that. So if we change that VMD and we change the droplet size and we cut it in half, we start with a 500 micron droplet, but you know, this nozzle's making some of these droplets that are 250 microns. So if we took the volume of a 500 micron droplet and we reduced that to 250 microns, but we wanted an equal volume, how many droplets would we have? Answer is 8. And so we look at that and say, well, why 8? You just cut it in half. Why is it not 2? Because we have 3 different axes across that droplet. So we have from left to right, from top to bottom, and front to back. So we would multiply that 2 by 2 by 2 and get 8. If we had a 500 micron droplet and some of them were 125, that's 4 times 4 times 4. That's 64 more, or 64 droplets that are a fourth of the size of what we started with. So droplet size starts to become an issue, and uniformity really comes to the forefront. And this is a pretty good way to visualize those droplet sizes. So if we look at 100 microns, you know, there's not very many things where we can spray 100 microns and really probably get it on the leaf. And so we look here and think of even 200. So all the white drops or dots represent the same volume. So there's 600 microns here and 100 here. It's the same volume. And then we see 250 and 300. And that's what it kind of looks like on a leaf, and some of the characteristics of each of these. If we look at the big droplets, low evaporation, because that's a big droplet. Very low drift, it's a big droplet. Canopy penetration, that big droplet can get through there in a longer drying time because it's, again, larger volume. The negatives there is we're not going to get great coverage. That droplet can hit that leaf, bounce off and splatter because of the volume, because it's big. And so it may reduce efficacy for a lot of the products. So you can see that the positives, negatives with each kind of micron size. And that micron size is going to be determined by the pesticide that we are applying. So I'm going to kind of read through this, or move through this a little bit quicker because we're, I think, closing in on time. But we need to look for good weed control and reduced drift control. And we have non-ionic surfactants or oil-based products or combinations of those that can help us get improved performance on the leaf surface. Again, something that we're trying to do is look at success. So we look at different things, and we're really just looking at a contact angle here. How well do they spread? So here's water. That's typically about a 93-degree contact angle with water. We see a non-ionic surfactant. Surfactants make water wetter, so we've got more spreadability there. We look right below that at silicon. It's an organosilicone type product. Super wetter, super spreader, great coverage from that droplet. And then we look at things that are high surfactant oil concentrates. Again, a little bit closer to water, has more contact, but it's not a super spreader type thing. So the adjuvant choice. Nozzles on fines, we've kind of talked about that a little bit. There's really 3 ways to actually manage drift control with a product other than a nozzle. We have thickeners or viscosity modifiers. That's what we usually call the drift reduction agents that we see required on the extend cropping labels. Then we have encapsulators where they kind of wrap that up. They really, the droplets up. They are sometimes very difficult to work with, and their efficacy is questioned because of how many times it might go through that pump. Then we've got spray droplet modifiers. They're not thickeners. They don't make it a thicker. They don't encapsulate, but they create uniformity. And that's the really big piece here, is creating the uniformity where more of the droplets that come out of that one nozzle are uniform. Jason, I know, has these videos. We can look at these and see that on the left-hand side, all this really dark cloud, those are fines that have been created. And here we have a droplet modifier. We see a more even, uniform pattern. That's the uniformity piece. Different tip, same kind of results. A lot of times we think we can just increase the pressure and blow it down into the canopy. And when we do that, we create smaller droplets and we create more drift that doesn't get down into the canopy. Again, different nozzles at the top of the canopy, the bottom of the canopy, different kinds of patterns that come through here. And then we put drift and deposition type products with that and get totally different results in coverage with different nozzles. Now back to this picture. This is the way that we've done that for years. Here's the new system. And here's really the difference. If we look at spraying horizontally, like we did 10 years ago, and what we see in the lab conditions, it's like a flag flying. It goes out from left to right or right to left. But in the field, that spray, that fan that comes out of the droplet or out of the nozzle is more of a sail. It can catch the wind. And that's what we're able to see with our new spray system. So this is what you kind of see. We create a bubble, and at some point that bubble ruptures, and when it does, it creates lots of fine. So we haven't accomplished anything yet. Just a schematic of how that works. We have a droplet, it pancakes because that's the easiest way to get through the environment or get through the air. It makes a long, thin kind of a tube standing up that catches the wind as we're moving through the field, or as the wind's blowing, creates a bag. The bag breaks. Lots of fines come out. This is what comes out of that in the laboratory. In a crosswind, it's not the uniformity that we see, that we want to see. And so even though this has drift control products in it, we have in a laboratory crosswind, as we're spraying, it changes. So this is more like field conditions. Just a close-up of that. Here's a bag that forms. A bag that's starting to break. You can see the ring. And then here where the bag has ruptured, and we see all those fines that are coming out. This is a story about guar and polyacrylamide drift reduction agents. This is what happens. They're all the same. It doesn't matter. But this is what we see out of our testing procedures and what we've presented to EPA, as a matter of fact, what we have statistical data on. So we can compare those standard testing, spraying that sideways, and a cross-flow wind condition, which is what happens in the field, and how much difference there is between what we've tested and what we actually see in the field. And then we put a droplet modifier in there, and we get a lot different results. So we create that uniformity again with a droplet modifier, so that the uniformity of that nozzle is more of what we want. So maybe just a couple minutes for questions if there are any. We're summing this up, and really anytime we make a spray application, it's about getting control, doing it right, accomplishing what we intended to do. And we think about a lot of things there. The chemical we're using, how we're calibrated, making sure we've got the right species, timing, important decisions, water volume, the nozzle choice, the pressure, the adjuvants we put in there. All those things come into success. So it's about what we're putting in the tank and getting the results that we want out of those. So Jason, I think that's the end of the slides. I hope we've gone through some things that make sense or something that brings up questions throughout that we can work through. So I'll turn it back to you.
Thank you, Dennis. We're going to go ahead and stay on schedule. We're going to go ahead and end this session and prepare for our next one. And then next session coming up be general CEU. We're going to talk about aquatic vegetation management. So give us just a little bit of time to make the swap over, log into the next meeting session. Again, Dennis, we thank you for your participation today. We thank you for the knowledge that you bring to Produce Cooperative. And we